Have you ever looked at a photo of a lawn and wondered, how could we turn that simple picture into actual, hard, scientific data? I mean, it seems easy, right? You just tell a computer to count the green pixels. But, as we're about to find out, the real world is a whole lot messier, and the solution is way more fascinating. Let's dig in. You know, the first rule of getting good data is creating a good setup. You can't just wander into your backyard and snap a random picture. Nope. To get results you can trust, you need a controlled environment, just like this greenhouse here. We're talking about totally consistent lighting, a locked camera exposure, a custom white balance. Basically, you nail down every single variable. So the only thing that's changing from one picture to the next is the grass itself. That's key. So here's our game plan for today. We're going to start by cracking the color code, teaching a computer how to see green. Then we'll hit our first big snag, the soil and shadow problem. After that, we'll give our data a morphological makeover, put our new method to the ultimate test, and finally, talk about why this all matters for creating smarter tools. All right, first things first. Our biggest challenge is trying to translate a very human idea, the color green, into a language that a computer can actually understand. And in the digital world, that language is all about numbers. Now, our secret weapon for this is a concept called hue. You got to forget about how bright or dark a color is, or how vibrant it is. Hue is just the pure, raw color itself. It's what makes red red and what makes green green. By focusing only on the hue, we can tell the computer exactly the pure shade of green we're hunting for. Okay, this is where theory meets reality, which I think is pretty cool. On the left, you've got that classic color wheel we all learned about in art class. Green is sitting right around the 64 mark on this particular scale. But on the right, that's how the software sees it. It unrolls that circle into a straight, linear scale of numbers. So our job becomes simple. We just tell the program, hey, I want you to grab every single pixel that falls inside this specific range of numbers for green. But, and this is a big but, there's a catch. There's no universal standard for this scale. One program might measure hue from 0 to 180. Another might go all the way to 360. So you can't just copy and paste the same numbers everywhere. You have to meticulously test and calibrate to find that exact numerical fingerprint for green that works for your specific setup.
So we have our tool, this hue filter. The logical next step seems obvious, right? Just select all the green pixels and we're done. But as we're about to see, that simple approach runs headfirst into a really big problem.
So here's our first shot. We apply a standard green filter and the software spits out a number, 53% turfgrass cover. And, looking at it, it seems pretty good. It really looks like we've captured most of the grass. But looks, well, they can be deceiving. The issue is what I'd call digital noise. What about those tiny little wet particles of soil that happen to reflect a greenish light? Or what about those really dark shadows deep between the blades of grass that aren't really green? A simple filter can get totally fooled by all this digital static. And this is what happens when we try to fix it the simple way. We make the filter stricter to try and exclude that soil, but look, we've also thrown out a massive chunk of the actual grass in the process. Our reading just plummeted from 53% down to 28%. We didn't fix the problem, we actually made it worse. We need a much smarter way to do this. And that smarter way has a pretty cool name, morphological transformation. This isn't just about filtering by color anymore. This is about teaching the software to think about the shape and the structure of the image, to clean up the data in a much more intelligent way. It's this brilliant three-step dance. First, we erode. Imagine taking a piece of super fine grit sandpaper to our selection. It shrinks everything just a tiny bit, and those little isolated pixels of noise, those soil reflections, they just get sanded away into nothing. Next is a step called morph open, which specifically gets rid of any thin, noisy connections. And finally, we dilate. This puffs all the real green areas back up to their original size, leaving us with a beautifully clean selection. And you can really see the difference in this close-up. I mean, look at the edges around those grass blades. They're so much cleaner, sharper, and way more accurate. All that random noise is just gone. But the important shapes of the actual grass are perfectly preserved. That's precision.
So a new technique looks great on paper, but it's only as good as its performance in the real world, right? We have to stress test this thing. Can it handle a nice, full, dense patch of grass? And can it also handle a sparse, really difficult sample?
First up, the dense turf sample. On the left, you've got the original photo. On the right, that's the output from our new morph process. And the measurement, 53% cover. It's clean, it's confident, and it's accurate. So far, so good.
But now, this is the real test. A super sparse sample, almost all soil. This is exactly where the old methods would completely fall apart, getting confused by all those soil reflections. But our morph method acts like a surgeon. It surgically removes all that noise and correctly identifies just 2.1% cover. It intelligently ignores the soil and hones in on only the actual grass. That is seriously impressive.
Let's just put the numbers right next to each other. For the dense grass, an older technique only saw 32% cover. Our new method got the more accurate 53%. And for the tough, sparse grass, our new method was again more on the money. The big takeaway here is that we've managed to create one single robust filter that works beautifully whether the turf is full and lush or sparse and patchy.
So, okay, we've just walked through a pretty technical process, but let's zoom out. What's the big picture? Why does developing a better way to count blades of grass from a simple photograph actually matter in the real world?
So let's recap. We figured out that hue is an amazing tool for zeroing in on a color. We also saw how simple filters get totally tripped up by noise like soil and shadows. But by using these intelligent morphological transformations, like erode and dilate, we can clean up that data and get a result we can actually trust, no matter what the lawn looks like. And here it is. This is the payoff. This whole highly accurate analysis was done using a normal consumer-grade camera. What that means is that this method makes scientific-grade analysis accessible to almost anyone. You don't need $1 million lab anymore. You just need a camera, a computer, and this really smart approach. It completely democratizes this kind of research.
It really gets you thinking, doesn't it? We just took a simple picture of grass and turned it into precise, reliable data. So the real question to leave you with is this. What other complex, real-world problems, everything from agriculture to even medicine, are just sitting there waiting to be solved if only we learn to look at them through the right digital lens?